Hello everyone. So today I'm going to talk about our work, a machine learning based elastic strategy for operator parallelism in a big data stream computing system, authored by Wei, Dawei, Shang, and Rajkumar, Buyya. So the content, I'm going to talk about includes the instruction, and then the IME stream architecture framework, and also the performance evaluation, and followed by the related work and the conclusion. So in recent years, and then big data has driven the rapid advances in distributed system, and there are basically two processing methods for big data. One is batch processing, another is stream processing. So for the stream processing, it is more suitable for real-time application. So the work of this in this paper is optimized based on the widely used Storm platform, but the entire design and also the strategy and the models are not only limited to the Storm platform. It can be applied to a variety of related stream computing environments. So and in this work, and we propose an elastic scaling strategy for operator parallelism, which is called IME stream. It supports self-adjustment during runtime and can effectively optimize resource allocation. And besides of that, and we provide a formal definition of scaling strategy for operator parallelism, and implement the complete process of self-adjustment in operation. And also we design the architecture of the parallelism strategy to solve the new bottlenecks caused by pluggable scheduling. We also evaluate the optimization performance of the strategy by metrics of execute latency and also process latency on Storm platform to prove the effectiveness of the proposal. So this is the ME stream architecture. As you can see, we designed an intelligent tuning solution model, and to solve the problem of parallelism of running instances without a manual intervention. So the whole process is like the first layer. We obtain relevant data of both, and then we move to the second, and then which is identify the parallel degree bottleneck, and then third one would be we generate a parallel parameter plan, and then followed by step 4, which is conduct parameter migration and then transformation, and then for the fifth step, and then we do the scheduling, and then sixth step we execute the rebalance command, and then so the seventh step, and then we just complete the resource distribution. Okay. The framework. The first thing we need to do is we need to identify the parallel bottleneck. So our strategy traverses the nodes and then execute the task in each topology in turn, and then counts the bottleneck existing in the current topology through the execute latency, and calculate the maximum execute latency at the bottleneck. So and we consider the communication bottleneck factors between nodes in different network environments, and then the strategy will sequentially traverses the nodes and then execute the tasks in each topology, and then counts the bottlenecks in the current topology and through the process latency, and calculate the maximum process latency as the bottleneck. Right, so those are the formulas, and we use it to calculate the bottleneck time of tasks, right, on all the nodes. I won't go through the detail, but if you're interested, you can please have a look at the paper. Okay. So once it is bottleneck is then identified, and then we design a threshold identification function, and based on the linear regression machine learning technique, it's easy to know when to perform the relocation. And after we get that function, and then we record the reference bottleneck by comparing the value of the threshold identification function and also the actual value in real time. So if the mean error between the value of the function and also the actual value is positive under some accuracy requirement, and then we just record the value as effective bottleneck value, and then we take the maximum effective bottleneck value in an interval as the reference bottleneck, and that interval actually can be set, and then by default it's 1 minute. So when that reference bottleneck occurs multiple times in an interval, and then the bottleneck time will be obtained by the threshold identification function, and then it is in the same order of magnitude. Right? So then we will perform the reallocation. Right? So, and there are two different type of priorities, and one is called bottleneck level priority. So this task with the highest bottleneck level gets the slots allocated first, and then followed by the remaining slots allocated to all the tasks with lower bottleneck levels. And this allocation strategy considers the weight of the bottleneck level, and is suitable for cases where the differences between bottleneck time of topologies is large. And then the second priority is parameter planning priority. And according to the bottleneck levels from high to low, and the previous executor number is added to the bottleneck level, multiplied by the coefficient, which is default equal to 1. So this allocation strategy controls the weight of the bottleneck level by coefficient, and is suitable for cases where the bottleneck time between topologies has little difference. So those are the steps explaining the parameter migrations and the conversion. So basically, we create a table, and then one that table has two columns, and those two columns record the nodes and then ports, on which is a pair of key. And so when we start the ME stream, and then we create that column, the table, and at the runtime, the current node and ports are saved in this table. And then before the redistribution, a new operator allocation generated based on the parameter schedule. And after completing allocation, the node and ports from the new allocation result, and then are assigned to replace the corresponding value in the routing table. And this is routing table. It's just it's not the routing table we thought in a router. Right? It just tells us how to migrate and then what kind of path we need to follow. Right? So after the N and the P are updated and then provided as the migration path, and for some stream instances, and then to the new schedule. Right? So when we actually do the instance scheduling, and then we need to call lots of methods. So for example, we need to call the need scheduler topology methods, and the get available slots, and the compute executes, and also the get alive assigned nodes and the ports and so on. So I won't go through each of them, but the again, if you're interested, please have a look at the paper. Right? So those are the methods again are implemented in the ME stream, and then so for example, the overriding slot can reassign and overriding bad slots, and so that it can be released, and also the migration path methods. Correct. So all implemented by us. So those are the all the IME stream related algorithms. As you can see, we got 3 algorithms. One is called the bottleneck identification algorithm. Another is a parameter plan, and then the last one would be a migration algorithm, and which also the steps, however, we already explained briefly in the previous slides. So to verify the effectiveness and the efficiency of the proposal, and then we do the some kind of performance evaluation. So the evaluation is done in an environment, and that environment is implemented based on the Storm 2.1.0. And also we use a computing cluster from the Alibaba Cloud Computing, and that cluster actually has 28 machines, and with one designated as the master node, and then and 2 designated as the zookeeper nodes, and the rest for the working as the supervisor. So those are the software, and then also the corresponding versions and of the environment. Regarding the parameter settings, and then so those are the parameters, and then so basically because our focus is to test the system performance when the spot has multiple executors, so the capacity value range is set to from 0 to 0.2. So when the value is close to 1, that means the load is severe, and then the degree of parallelism needs to be increased. And then also when the field value is not 0, so that means the load is serious, is too much overloaded, and then there are tuples that experience failures or timeout. Right? So this is when we run a word count instance, though that's the performance results we get. So this one, so we execute latency. Execute latency reflects the overall execute time for all when we run all the DAGs. So the smaller, and then the latency, and then the stronger the processing ability. Because so the average, as you can see, the average execute latency by IME. So this is IME as our method, and that is the default scheduler. That's by the Storm, and after the application enters a stable stage, and then from the 28th minutes to 15 minutes, as you can see, the latency we got is like 2.3886 ms, and also this is the latency for the default default scheduler, which is 8.3 something. So this is the average, as you can see, and then the execute latency by our method is lower. And then there's another performance result, and then this is about the process latency, and it reflects the overall processing time for all running DAGs. So the smaller latency, and then stronger of data processing ability of the system. So the error, as you can see, our curve is here, and then that's the default Storm scheduler. So the average process latency by IME stream is 14 something. So it's here, ms, and then but for the default one, the Storm default one would be 50 average would be 52 ms. Again, it's after the application enters a stable stage, which is from the 38th to 50 minutes, and I'll demonstrate the process latency of our proposal is lower. on this on the given word count instance, and then when the input rate is stable, and also we collect the statistics or execute the delay, process delay, and also the total delay data sets of the default scheduler, and also our ME stream optimization strategy. So that one is the storm latency produced by the default scheduler, and this one is our methods latency, and we can see this comparison. So for the related work, we pick up the state of the art research works and then compare them. So we pick up 4 of them and focusing on the key features, and they provide. For example, the parallelism machine learning support or not, and then support the cost saving or not, and then resource saving or not. So and then they get a different piece of research works, and they support different features, and kind of our proposal supports almost all those selected features. So in summary, the reason why we do this research is only because it is not transparent for Storm users to use API to set the parallelism for operators in the topology at runtime. So users need to run the API frequently to change the configuration of their application. So Storm users also they don't know how to optimally adjust the parallelism. So and then we use the machine learning model and to try to learn some information to achieve a better parallel migration path. The model can achieve a better effect in terms of resource allocation without manual intervention, which has some certain learning ability. And also, Storm distributes instances to work program, and the work program nodes in a round robin manner by default. So the number of configured work program is still evenly distributed. So the instance scheduling we design can achieve better compatibility with the intelligent tuning scheme under the premise of ensuring good generalization. Good. All right. So that's all. Thank you very much.